Hello there, welcome back to another video. Today, we're going to be talking about implicit differentiation. Now, it sounds really complicated, but the thing is, implicit differentiation is actually one of the easiest topics in calculus. And it's also one of my favorites, because it's quite simple to do, and it's also quite clever, and you'll see what I mean. So, let's get straight into it. Before we do anything, we need to figure out what exactly implicit and differentiation mean. So, differentiation is just another way of saying derivatives. Okay, and we know all about derivatives, right? Okay, and then what about implicit? Well, implicit means something that's implied, maybe even something that's hidden. Okay, great. So it's hidden derivatives? Yes, and I'll show you what I mean. Let's do this question here. Y squared is equal to 3x squared plus x. Okay, well, we can do the right side pretty easily, right? This is just simple power rule. So let's do the right side first. Whenever we apply derivatives, we want to take each individual term of a polynomial and take the derivative of it. Now, y squared is a bit tricky, so we'll get back to that. That's our main implicit differentiation part. But x squared we can do right now. So we can say y squared is equal to, and then the derivative of 3x squared will be 6x plus, and then derivative of x is just 1. Okay, we've taken the derivative of this. Now we need to figure out what's the derivative of y squared. You would think that we could take the derivative of y squared just like how we take it of x squared. So y squared will just become 2y. But that is not the case because, and I'll explain it here. Another way we can write y is as f of x, right? And that's a function, right? So y is a function. Okay, but what's the point of that? Well, let's plug in f of x instead of y. So f of x whole squared is equal to 6x plus 1. But the thing is, I now have a function inside of another function, right? So what rule are we going to use when we have a function inside of another function? You're right, we use chain rule. Chain rule says that for some function g of f of x. So over here, our f of x's are the same. And over here, g of x is the same as x squared here. So we have an outer function and we have an inner function, right? So then we can say chain rule says that it's g prime of f of x times f prime of x, right? Okay, that makes things easier. So how are we going to use chain rule here? Well, let's go back to a function. It's f of x squared, right? So we can rewrite this exactly the same way. So we get f of x squared. And then this is the derivative of. Same thing here, derivative of f of x squared is equal to. And then we take the outside function and take its prime. So derivative of x squared is 2x. But instead of plugging in x, we plug in the inner function, which is f of x, times, and then we take the derivative of just the inner function, so just f of x. Now we don't know exactly what f of x is, but we know it's a function. So we can just say it's f prime of x. Same thing as over here, right? So that right there is our derivative of y. And now we can just substitute back in y instead of f of x, and we'll get our final answer. So we know f of x is y, so we can say it's the same as 2y times, and then we can write f prime, because remember we talked about this in the first video. The way we can write a derivative is f prime of x, but we can also write it as dy over dx, right? So we get 2y times dy over dx. Great. Okay, so let's plug this back into our original function. So we get 2y dy over dx is equal to 6x plus 1. And that right there is the derivative of our function. So what have we learned so far? Well, we've learned that whenever we take the derivative of y, so for example y squared, we always need to make sure that we account for the fact that it's a function, right? So we always need to put a dy over dx in front of the actual derivative, right? So that's what we've learned here. We always need to put a dy over dx whenever we're trying to find the derivative of a variable that's not x, and we're differentiating with respect to x. Let's do a practice problem to really get this set in our heads. Okay, here. Find the derivative of y squared plus y is equal to ln x plus 3x squared. Okay, well, we need to apply the same rules we've just learned. So let's differentiate the x's first, and then we'll talk about the y's later. So we'll leave y squared plus y in the same place is equal to derivative of ln x is 1 over x, and this is probably seen in most formula booklets, so you don't need to worry too much about this. But for AP students, you should memorize this. Plus, and then derivative of 3x squared, 2 times 3 is 6, 6x. Okay, now we need to take the derivative of the left side. So on the left side, let's do y squared first. So we've just done this one actually. So it'll be 2y, and then always remember the dy over dx. This is the implicit differentiation we're talking about. Plus, and then we take the derivative of y. Derivative of y is just 1, and then always remember the dy over dx is equal to 1 over x plus 6x. Okay, well, we're almost done, but actually when we try to find the derivative, we want to isolate dy over dx and put it on one side. So let's quickly do that. One thing we can do over here is we can factor out dy over dx from the left side, so we can keep it as one variable. So we can do dy over dx 2y plus 1 is equal to 1 over x plus 6x. And then we can actually simplify the right side a little bit. This could be the same as 6x squared plus 1 divided by x, right? And then on the left side, we leave it the same, dy over dx, 2y plus 1. And then what we got to do is we got to divide both sides by 2y plus 1, so we can isolate dy over dx. So we got dy over dx is equal to 6x squared plus 1 divided by x times 2y plus 1. And that right there is the derivative of our function. And what this basically means is if we plug in any value of x and y into this function, we can get the slope of that function at any given point. So this is really helpful in slope fields, and it's also helpful in related rates, which basically talk about variables changing across time. And we'll actually go into that next video. But implicit differentiation is a really good first step into a more complicated calculus. But in and of itself, it's quite easy. And I hope this video sort of helped you in understanding that. So I'll see you in the next one with related rates. Bye-bye.